All right. Hello, everyone. Welcome to join the third Innovations in Digital Design webinar. The webinar features two exceptional speakers. One is Dr. Xin Yan, and one is Zhi Albert Li. So they will discuss their research and application in structural topology optimization, incorporating subjective preference. The first one will welcome Dr. Xin Yan to discuss design details control strategies for structural topology optimization. Dr. Xin Yan is an architect with a comprehensive background in mechanics and computer science. Currently, he's a postdoc researcher at Future Lab and Tsinghua University. He received his PhD in architecture and urban design and Master of Architectural and Civil Engineering from the University of Chinese Academy of Science in 2022 and 2016, respectively. He's graduated from Theoretical and Applied Mechanics at the University of Science and Technology of China in 2013. In 2019, he also carried out his research work at Structural Topology Optimization at the Center for Innovative Structure and Material at RMIT University, Australia. Let's welcome Dr. Xin Yan to share the screen.
Okay, thank you for the introduction. And let me share my screen. So can you hear me and see the screen?
Okay.
Okay. So it is an honor for me to show some of my works about the topology optimization design. And good morning, afternoon, and evening, everyone. I'm Xin Yan from Future Lab at Tsinghua University, and today my topic is about the design detailed control strategies for structural topology optimization. So, this is just the description of my work and study histories. So, the background of this research is that in the past 20 years, there are so many famous architectures or structural components generated by the topology optimization algorithms. As you can see, there are 7 very famous examples of the design. So each one of them has a very organic and elegant form with the very high structural performance. So what is the topology optimization? The topology optimization method is just with a very clear and simple logic. So as you can see, the left one is the working flow of the BESO method, which means bi-directional evolutionary structural optimization, which is developed by Professor Yiming Maxie, which is the supervisor of me and Dr. Li Zhi. So he just developed this method to optimize the structure under some specific loading case. As you can see, there is one example about the 2D cantilever. Firstly, we can just make a 2D plan design domain, and we fix the left boundary like the right lines. And then we just add the load case, a point load in the center of the right side. So with the help of finity element analysis, which is FEA for short, we can calculate the mechanical values in all the elements. So each element have its own mechanical values, and then the algorithm can just compare the mechanical values, and we can choose the element with the very low mechanical values to be removed from the whole design domain. With this method, we can just reduce the materials in each step. And when we just go in this loop, we can optimize the whole structure. So you can see there are 6 classical streets for the whole design, and then finally we can generate a very you can say it's a very special and logic structures which can also have a very high structural performance. So, but the conventional topology optimization has their own problems. They have limited application conditions in the early stage of the architecture concept design, because when as a designers, when we design our own work, we need to compare our own design objects with the structural preference. So this is a very important thing for us, because if we just depends on the computer and just use the computer, what computer tell us which one is good and which one is bad, is not work of us. So, but when we use the conventional topology optimization, we usually do something like this one. Firstly, we make an initial model like the green one, and we just maybe we can image what's the outcomes, what's the final results. We want to the final result like this one. There are some standard structural components with very small holes overall design domain. And then we just start the optimization algorithms, and we have nothing to do but wait, and wait. And finally, the algorithm finish is optimization, and we just want to get a very good design, but the outcome is like this one. We can see the final result the computers give us is a very it's hard to say, is with the highest structural performance, but is not what we want. So the question is, can we pre-design the details before optimization, and how to control the design features with topology optimization? So this is the intentions of my work, and to finish to achieve these goals. Firstly, I just construct a framework, BESO framework, oriented to the architecture design. So in the conventional BESO logic, we just write Python code and random in the Python environment. We have nothing to choose, and then in my work we just divided the whole logic into several parts. Firstly, we can make a model in the Rhino or SketchUp or 3D Max or just any other 3D softwares. And we can use the Grasshopper or some scripts to transform the 3D model into some TXT files, so which contains all the geometric information about the model, and we can transfer the TXT information into the FEA platform, just like Abacus, and then use the Python code to control all the loop and generate the TXT files contain, which includes the results information, and then we just transfer the TXT files to the Rhino environment back and get the final 3D results. With this framework, we can easily generate a very beautiful initial design domain with a freedom surface or with very complex forms. And then we can just use the grasshopper to generate its calculation network. And we can get all the information about the FEA elements we need and then transfer the information into the TSC files and transfer the numbers, the values into the BESO loop. So with this framework, we just design and fabricate some installation like XForm 1 with Dr. Nick Bao and Professor Max Xie, and XForm 2 in the 2019 at Barcelona exhibition, also with the Dr. Nick Bao and Professor Max Xie. And we also do some computation, which means structural computation to generate the most highest structural performance result. So this is the basic logic of the framework, but this is also not fit our goal about the pre-designed form details. So I just changed the framework with the right part, which is artificial coefficients files. This one is just contains some parameters. And with this kind of parameters, we can change the basic BESO logic and to add our design goals, our design preference to the structural optimization. So there are 6 new algorithms I developed in the past 2 years. And the first one is the original BESO logic. So you can see the right part is the artificial coefficient files I made. And we in this algorithm, I just add some parameters into the topological optimization algorithm, and then just integrate our design concepts with the structural calculation and mix them together to get another design, which is at some level can fit our design goals. So the first one is geometric constant. You can see this is an example about the high-rise building. We just fix the bottom boundary and add the wind load at the 2 sides of this building. And with the original BESO method, we can just optimize the structure like this one. So you can see in the final result, there are some asymmetrical parts here and here. So why we get asymmetrical parts? The reason is one is because the calculation errors in the computer, and then the most important one is when we reduce the materials, which means when we remove the elements, maybe the elements in the symmetrical positions are not reduced at the same time. So when one element is reduced and the other one is still here, and then from that point, the following results goes to the asymmetrical. So I just made a SYM BESO, which is symmetrical modified BESO method. In this method, I just coupling the symmetrical elements and add their mechanical values together to generate a new value, which means sensitivity number. And then based on the new sensitivity number, I can just remove the symmetrical elements together. So in each part, in each step, we can get a symmetrical symmetrical results. So you can see with this algorithm, we can always generate the symmetrical result. And the second one is with the similar logic. When we optimize a periodic structure with the conventional BESO method, it's hard for us to generate a very regular outcomes because there are so many elements in the periodic parts. So we need to calculate all the elements values together and then remove them or preserve them at the same time. So with the CYC BESO method, we can generate our results with the periodic features. So you can compare the outcomes. This one is generated by the original BESO. So you can see there are some unperiodic parts here. And then with the CYC BESO, we can just add the periodic constraint to the algorithm and generate a form with the periodic filters. And the third one is just a little method because this is still with some calculation errors in the FEA process. When we generate a design under the gravity, the BESO method may face a problem like this one. So when we in the middle of the evolutionary parts, evolutionary process, we can just generate some small parts, which has no supports around it. So in the next calculation, this small part will just fall down without any support. So if this thing happens, all the FEA calculation will stop because there is a very big displacement. So to deal with, to solve this problem, we just need to remove the isolate part before the calculation start. But the question is how we can find the small parts without any supports in the optimization algorithm. So we just use the depth first search method to search for the isolate part. And then with the DFS method, we can just we can just select which one is the small part without any supports and remove them firstly, and then transfer the remaining structure to the next calculation. And the second strategy is the pre-design with multi-radius. Yeah, the multi-radius BESO is just a change a very important parameter named RMIN in BESO method. In RMIN BESO, in the conventional BESO method, RMIN is just a very important parameter to control the local size in the final result. This value is like it's like the size to smooth the local mechanical values. So with the RMN value, we can generate a part. We can generate the final part with the similar size. So in the original BESO method, we can only set the one RMI value for each element. And then we just generate a part with the similar size around the whole design domain. But if we can encrypt the different element with different RMI value, we can pre-design the local size in the final result, like the diagram here. So, which means if this part is if this element is encrypted with a bigger RMI value, and the right one is with the small RMI value, then with the MR BESO method, we can generate a final structure with the very huge blue parts and very small red parts. So with this kind of method, we can just use the RMI value to pre-design the final features in the optimized result. So just back to the 2D cantilever algorithm. So if we add the different RMI value from 10.5 in the of the left part to the 1.5 millimeters in the right part, we can generate a final result like this one. You can see with the very big RMI value on the left, we can generate the very huge structural components here. And with the small RMI value on the right, we can generate some slender parts. This is generated by the original BESO method. So you can see the difference. Also, the building, the high-rise building example can be generated like this one. With the MR BESO method, we can just set the bottom RMIN value about 3 meters. Oh, sorry, 15 meters. And the top one is with 3 meters. So you can see the structural features from the bottom to the top is from the huge to the small. So this is the shell dome examples. The deep parts, deep right parts means the elements with a bigger RMI value, and the light pink part means represents the elements with the smaller RMI value. So we can just pre-design the relevant geometric features before the optimization starts. So similar, we can get this one. You can see the fifth one. Red part means the element is encrypted with a bigger value, and we can generate a very huge components here. And the blue part means the elements are pre-designed with the smaller RMI value, so we can just very small components near it. And the third strategy is pre-design with a multi-volume. So in the original BESO method, we have only one volume fraction, which means maybe if you set the volume fraction as 15%, it means you will remove 50% elements away and hold half materials in the final result. But if you just have the only one volume fraction around the whole design domain, sometimes it will happen like this one. So when the original BESO method optimized the whole design domain, there are some parts totally void and some parts with totally solid, because the right, maybe the left part is more important for the structural performance, and the right part is not that important. But for the function, for the architectural function, maybe sometimes we need some materials near the right part, and we also need to dig some holes near the left parts, like the blue one and red one. So MVP, so we can with MVP, so we can just add more local volume fractions into the different parts, and the algorithm can optimize at the same time, but reduce different materials in the local parts. So this is a 2D cantilever example. When we just develop the whole design domain in two parts, and we can maybe we can just change the different local variables. Maybe from the case file means the each part have the same volume fraction, and case one and case 9 have the totally different volume fraction. So you can see when we add the volume fraction of part 2 bigger, we can in the case 9 we just have a very huge structure in the right, and very slender components in the left. So with the different in the subdomain diagram and with different local volume fractions, we can generate a totally different design, and we can control the local materials in the final result. So this method maybe is very important for the high-rise building design, because in the original BESO method, we can only have the whole one design domain, and we generate a structure have more materials at the bottom, and there are very small components on the top. So if we just divide the whole design domain into several parts, like 6 sub-design domains, or 12 sub-design domains, or 18, we can generate different designs. So with the sub-design domains, we can just calculate their own volume fraction at the same time. So we can dig some holes in the this one is a very good example for compare the original BESO with the MVP BESO. With the original BESO, we can generate final result like this one. But for the building design, the bottom part is very expensive we must dig some holes as the doors or windows to let the people or light come in. But for the structural performance, if you dig some holes at the bottom, will have a very big effect on the structural performance. So if we just divide the whole design domain into 12 levels, we can make some bigger holes and add some more windows in the bottom parts. Also have some more materials, structural materials on the top. That's what we want, because when we design a building, we can it's not only depends on the structural performance. We also need to compare other structural requirements. Not structural requirements. We need to think about the aesthetic or the function requirements. So this is an example about the shell design domain. The shell design with different sub-design domains, we can generate different parts. So you can see if you have a very in the original BESO method, we can generate a structure like this one. So the center part have no holes inside it, because the center part is very important for structural performance. But if we just design a shell roof of a building, maybe we need to dig some holes near the central part. So you can just add more sub-design domains in the initial design, and then with the different volume fractions, we can just dig some holes near the central part logically. So also we can generate some very special shell design domain with the MV-BESO method, because we can draw some different patterns on the top, and then set the different local volume fractions of the different parts. So we can pre-design the whole the geometric features of the whole design. So you can, if you want to make some big holes at this part, you will just set a very low volume fraction of in this part, and then if you just maybe you want to some bigger structures here, so you can just add the local volumes fractions to the a higher level. So this example is about the Olympic National Stadium. When we use the BESO method to generate it, the first one is the example we are familiar with. This is the original design of the bird nest, and the level 2 is the design with the original BESO method. So you can see this design is the best one from the perspective of structure, but it's not a good design from the perspective of architecture, because there are so many materials at the two corners, and very big holes in the middle part, which is not look like don't look like a bird nest. So if we use the MV-BESO method, we can just divide the whole design domain into many parts. So like 25 subdomains, 100 and 400. So with MV-BESO method, we can generate a final result with more slender structural components and with more small holes over all the structure. And the last one is pre-design with multi-weight. In the BESO method, the very important value is the elemental mechanic value after FEA calculation. So this value is the parameter for us to choose which one element should be removed and which one should be contained. But this value in the original BESO just care about the loading, the structural performance. And if we want to add maybe some drawing or some diagram into the algorithm, we can add another value into the calculation of the sensitivity number, like this one. So this one is about the loading, the structural loading. And this one is about the graphic parts. You adjust a human, add some drawing to it. So this the MW BESO can just compare these two information and mix them together to generate some different designs. This 2D cantilever can just if we add a drawing like this one, which means in the left parts we add arrows like this one, and we maybe the designer just need to add a structure near the left parts, but components like this has very limited contribution to the structural performance. So if you add this pattern, you can generate parts in the final result with MW BESO. And if you just reduce the weight of the graphic, you can just return to the original BESO result. So MW BESO equip you with choose. You can just reduce the materials at any time, at any level. So if you have a very big goals to have a very, I must have components here. You can just add the weight of graphic to a bigger value. And if you just want to have a try, if the components is really unimportant for structural performance, you can accept it can be removed. You will just need a weight of graphic to a very small value. So with this kind of method, you can add some geometric features inside the final result. Also, if you don't want to add graphic patterns, you can also add the different ways about different loading cases. So for the dome design, this one, the bottom left one, is generated only with the gravity loading. And this one, the first one, is only with the torsion in the center. So you can see the totally different patterns. For the first one, which means the torsion in the centers, it will generate some curved parts like the red lines. And if you just calculation and gravity, you will generate some straight components from the boundary to the center. So if you change the weight of gravity or torsion, so you can just adjust the curve, the structure local components from curved lines to the straight lines. So this is a real project designed by the MW BESO in 2020 at Shanghai in Tongji campus. So when we designed this installation, we just made a initial design domain like this. So it's a wall, it's a concrete wall. And we just add a first load is shear force on the top, and add two windfalls at the two different surface, and fix the three points. So when we use the original BESO, we just generate the final design like this one. This one is not what we want, because the top parts have no holes, but the middle parts have so many big holes. So we just use the 2D example to generate a 2D optimized pattern, and then transfer the pattern to the MW BESO and generate the the weight parameters, which is the artificial coefficient files to the MW BESO, and then we can just compare the three information and mix them together, which means we set the weight of the loading case to the 99%, and the artificial intervention pattern with the weight of only 1%. But the final result is totally different from the original BESO design. So you can see with this settings and with MW BESO, we can just add we can just generate a design like this one. It's totally different from the original BESO, right? It's totally different from this one. So if you compare the MW BESO optimized result with the form or with the patterns we transfer to, you can see the MW BESO add a structure components in the middle to support the whole structure and add the whole structure, encrypt the whole structure with a higher structural performance. So this is the final installation in Tongji Compass. So that's the work of mine in the 2 years, and that's all of my today's presentation. Thank you.
Thank you, Dr. Xinyan. And we're going to ask some questions about Dr. Xinyan. And if you have any questions, please feel free to unmute yourself, or you can type for the comments. And if there is any questions on YouTube live, when you're if you're still looking at it, you can type in the comments, and when we see, we will tell Dr. Xinyan. Thanks.
Hello, can you hear me?
Hello. Yeah.
Hello. Hello, Dr. Yan. Thank you for your amazing presentation. And I have a question for the MWBSO for in your bird nest example.
Yeah.
How's the performance loss when you use different resolution resolution of subdomain? Performance loss.
In this presentation, I didn't add the information about the value, the structure loads. So if you, but the information is, so let me open my paper.
Okay.
It's to give the information about the component, the structure loads. Yeah. So, sorry.
This one. Just okay.
This one. So this is the initial design, which is the real project, and this is the BESO parts, BESO result, and this is the 3 design with 25 sub-design domain, 100 and 500. So with the different loading cases, we generate, we just compare all the results with the BESO method. So you can see at the earthquake force, maybe the BESO method is the good one, yeah, the best one.
Yeah,
but for the torsion in the center, you can see the MV BESO is the best one. And initial design is also good. But for the gravity MV BESO is also good for compared to these two. So I think it depends on what you want to optimize, because in this example, I just add all the loader case together to reduce the materials. So I think the MV BESO can generate the structure with small holes, so which is much better for the torsion in the center.
Okay, understand.
Yeah.
Thank you for your answer. And I have another question, that is, when you developed this algorithm, I remember you used Python. But when I use Python, I noticed that only float numbers are allowed, not double. But when we use BESO method, we have a design variable. We need a very small design exponent. Is that? I remember that. Yeah. But how you use Python to support this very small number, because it may execute the limitation of float number.
Actually, I haven't encountered with the problem about the float limitation.
Okay.
So,
We
yeah.
can discuss later.
Yeah. But I can see maybe you can try to identify the float number and then just calculate back to the result. So I mean, in the middle process, you can just amplify the float number if the float number is too small, and you generate it, you calculate it, and then go back to the real value. I mean, divided the value. Yeah.
Okay, I think this is a question about numerical accuracy, but now it's
Yeah.
okay. I understand. We can discuss later. That's fine.
Yeah,
Thank you
yeah.
for your
Thank you.
That's all my questions. Thank you.
Thank you.